We are diving straight into the paper today. Reward forcing. Efficient streaming video generation with rewarded distribution matching distillation. This research really tackles one of the most frustrating failures you see in real-time generative video. That moment when a highly detailed video just starts to freeze or the action gets stiff, what the paper calls frame copying.
Yeah, exactly. And this team has delivered a really powerful solution aimed right at the heart of that specific problem. They've managed to distill these massive, slow, bidirectional diffusion models into a lightning-fast, few-step, autoregressive student model. And they did this through two really core technical innovations.
Okay, let's hit them. The first is EMA Sink. It's a dynamic state packaging mechanism. So instead of the model getting, anchored to a single starting image, EMA Sink continually updates and compresses the model's historical context. This ensures long-term consistency, but still allows for recent dynamic motion.
And then the second key innovation is Re-DMD. That's rewarded distribution matching distillation. This is where they inject a kind of quality filter into the training process. They use a vision language model as a reward function to aggressively prioritize training on the samples that actually show high natural motion.
And the result of all this is, well, it's truly state-of-the-art video quality. You get dramatically improved dynamic sequences and the ability to achieve true real-time streaming performance at a blazing 23.1 FPS. And that's on a single H100 GPU. So that's your critical 1-minute takeaway right there.
That combination of speed and quality is really what makes this research so important for anyone looking at building, say, dynamic or interactive virtual worlds.
Exactly. Okay, so for the researchers and engineers listening, let's set the stage. Let's start with the foundational challenge here. If you want high fidelity, the established heavyweights, the large fusion transformers or DITs, they're fantastic. But they use bidirectional attention, which means every frame has to talk to every other frame all at the same time.
That introduces this massive latency,
Yeah.
making them totally
Completely unusable. Yeah, for any real-time streaming application, it's a non-starter.
right.
So the immediate response from the research community was to shift towards efficiency through distillation. You take the knowledge from that slow, powerful teacher DIT, and you distill it into a smaller, faster student model. Models like CauseVid or self-forcing, they adopted an autoregressive approach, so frame by frame, using sliding window attention and the key value cache, the KV cache, for fast sequential inference. But the moment you go autoregressive, you inherit a classic AI problem.
Yeah.
Error accumulation. I mean, since each frame is conditioned on the output of the frame right before it, which might be slightly corrupted or noisy, those errors just start to propagate. They drift over time, and that can destroy your long horizon consistency.
Right. And to combat that drift, prior work adopted what's called the attention sink mechanism. The idea is actually brilliant in its simplicity. You just retain a set of static initial tokens in that KV cache throughout the entire generation. This gives you a stable, unmoving anchor for the attention computation. It ensures the model always has a reliable reference to the start of the sequence, which helps a lot with that long horizon drifting.
Okay, but if the attention sink solves that long-term drift problem, what's the inevitable trade-off? What's the downside of using a purely static anchor like that?
You've just nailed the critical flaw. That constantly preserved static initial token creates an unavoidable, very strong bias toward the starting frame. I mean, think about it. If your model is forced to perpetually pay the most attention to the very first thing it saw, it's going to struggle to evolve the content naturally.
And that's where we get those diminished motion dynamics. The stiff sequences, the visual flashbacks, the video literally starts copying frames from the beginning, even if it's 20 or 30 seconds into the generation.
Precisely. And a key limitation of the standard distillation method, vanilla distribution matching distillation, or DMD, is that it can't fix this. Because those degraded stiff samples, they still have high visual quality. So they fall close enough to the teacher model's distribution to satisfy the loss function. Vanilla DMD just has good image quality, close enough. It just lacks the discrimination to specifically push the student model toward dynamic fidelity.
This brings us squarely to the first major technical solution in this paper, the EMA Sink, a novel state packaging mechanism designed specifically to get around that static sync trap, especially for ultra-long videos.
The trick they use here is, it's really elegant. A traditional sliding window works by just, tossing out the oldest frame when a new one comes in.
Yeah.
EMA Sink says, wait, don't throw away that history entirely. Instead, it actively uses the information from those evicted frames to maintain a compressed global state, which they call ZL dollars in the KV cache, using an exponential moving average.
That sounds conceptually almost like how human memory works, actually. You might vividly remember what happened yesterday, but details from 2 years ago are compressed and smoothed into a general memory, not a perfect snapshot of that first moment.
That is a perfect analogy. The static sync is like having one perfect photograph that you're forced to look at constantly, and it stops you from moving on. The EMA Sink, though, creates a smooth, weighted summary of everything recent that has happened. By continually integrating the dynamics from the frames that are being evicted, it ensures the global context is always current and dynamic, not static.
So if I'm getting this right, when the oldest frame in the window gets evicted, its key value pair is fused into those compressed sync states. And there's a momentum decay factor, alpha, that controls how much the old context fades versus how much the new context gets incorporated.
That's exactly right. And the crucial benefit for you, the engineer, is that this design compresses the effective global context. So it maintains that long horizon consistency that prevents drift. But because it's a moving average, it's also integrating recent dynamics. It keeps the past present, but fading and dynamic. And that prevents that perpetual over-attention to the initial frame.
Then this continuous context update, it doesn't come with a major computational penalty, right? Which is obviously vital for streaming.
Absolutely. Because they are just fusing existing key value tokens, the EMA Sink enables token eviction and context update in overtime time. Very low overhead. This means the model can support indefinitely long video generation because the memory usage stays constant no matter how long the sequence gets. It's a low-cost, continuous context renewal. That's the architectural linchpin.
But using a smoothing factor always feels like a bit of a risk. You mentioned that alpha value is needed to balance consistency, but isn't any smoothing factor just going to risk, I don't know, permanent context blurring or even increasing the drift if the value isn't perfectly tuned?
That's the exact question their ablation study addresses. And they found this balance is incredibly sensitive. If the coefficient alpha GAR is too low, meaning the old context fades too quickly, the drift goes way up because you lose your anchor. But if alpha GAR is too high, it acts too much like a static sync, and you lose all that dynamism. The paper identified a sweet spot, specifically 9D33, which they found provides that perfect balance between motion fluidity and long-term consistency. It's a delicate piece of engineering to get right.
Okay, so that covers the architecture. Now let's turn to that second challenge, quality optimization. Because even with the EMA Sink preventing frame copying, the student model still needs to be explicitly guided toward generating interesting motion. Which brings us perfectly to the second innovation, Re-DMD, Rewarded Distribution Matching Distillation.
Right. Standard EMD is all about fidelity to the teacher, minimizing divergence. It's asking, is the student's output similar to what the teacher would have made? The inherent limitation, as we discussed, is that the teacher's distribution includes a lot of perfectly plausible, high fidelity, but ultimately really boring and static sequences. Vanilla DMD has no way to prioritize the dynamic content. It just treats every part of the target distribution equally.
So Re-DMD is basically distillation with an automated quality filter built in. It makes sure the student only learns from dynamic, high-quality examples, even if low-quality, static examples are technically plausible.
That's the conceptual takeaway, yes. They introduce preference or quality awareness right into the distillation process itself. They reweight the standard distribution matching objective according to the sample's motion quality. And this framework is based on something called reward-weighted regression, which reformulates reinforcement learning as a probabilistic inference problem.
Can you break down that RL connection simply? Why is this so much more efficient than, say, traditional RL fine-tuning?
Okay, so if you use traditional reinforcement learning -RL to fine-tune a model for motion, you'd be generating videos, getting a reward score, and then trying to backpropagate those gradients all the way through that entire noisy reward process. That is computationally massive, it's slow, and it's often very unstable.
A real bottleneck.
Exactly. The brilliance of Re-DMD is that it avoids this dynamic steering completely. It treats the reward not as a constantly changing landscape you have to navigate, but as a static weighting factor. They generate their samples, use a VLM, specifically video lines motion quality metric, to calculate a reward score, $2.
Yeah.
And this score is then used to weight the standard distribution matching gradients.
So the distillation loss is basically saying minimize the divergence from the teacher, but pay dramatically more attention to the gradients that came from samples we already know had high motion quality.
You've got it. This implicitly biases the model's output distribution toward those high reward, high dynamic regions. They completely eliminate the high computational cost and the instability that comes with trying to backpropagate through a noisy reward model. It's using RL principles, prioritizing successful outcomes, but it's applied through a much more efficient distillation mechanism.
And just like with the EMA coefficient alpha, they also introduced a crucial balancing parameter here, the regularization term beta litter. It modulates how much influence that reward has. How sensitive was that trade-off?
Oh, it's critical because you're essentially trading dynamism for coherence. If you push the dynamism too hard, you just get exciting but chaotic videos. They found that an optimal balance between getting the most motion dynamics while maintaining visual fidelity and coherence was achieved with beta 12.2.
I can just imagine what happens if you get that wrong.
Right. If betas was set too low, the reward term just dominated the loss. The model became obsessed with generating high dynamic scores, but at the expense of background consistency, smoothness, image quality. The video would be incredibly dynamic, but look like, visual soup. But if Detos was too large, the reward term didn't have enough influence, and the dynamism score stayed low. It's really the art of balancing that generative power with structured control.
That provides fantastic clarity on the engineering foundations. Now let's look at the benchmarks. You, the listener, you need to know where reward forcing actually sits in the current research landscape.
On standard short video generation, we're talking 5-second clips. Reward forcing achieved an overall vBench total score of 84.13. This positions it as the state-of-the-art across all the comparable baselines, including COSVID and long-live. It really proves they successfully injected that robust motion without sacrificing overall sample fidelity.
But the efficiency metrics are truly the triumph here, I think. They validate the entire streaming architecture.
Absolutely. The real-time speed of 23.1 FPS on a single H100 GPU is just phenomenal. That's a massive 47.14x speedup over older models like Skyreel's V2. And it's even a noticeable 1.36x speedup over the existing fast baseline, self-forcing. And crucially, they achieve this while using the smallest attention window among all the compared methods, which just confirms the memory efficiency of that EMA Sink mechanism.
And that stability and dynamic control carries over to long video generation, too. When they tested it on 60-second generation, reward forcing achieved a vBench long total score of 81.41, which significantly outperforms high-consistency models like long-live.
The dynamism metric really tells the story here. Reward forcing hit a dynamic score of 66.95. And to put that in perspective for you, that represents an incredible 88.38% boost in dynamic amplitude compared to previous state-of-the-art benchmarks that were focused on long videos. So they got high dynamism while also minimizing quality drift over a full minute.
And the training trajectory just confirmed that the whole Re-DMD approach works efficiently. After about 100 GPU hours, the dynamic score had already surpassed the high-consistency, low dynamism models. By 150 GPU hours, it had outperformed the high dynamism models that typically suffered from that severe drift. It really did find the sweet spot efficiently.
And this whole framework, it's built for interaction, which is really where the future of generative media is headed.
Okay, let's discuss that application. Beyond just benchmarks, what does this level of real-time control actually enable?
It enables interactive video generation where a user can intervene midstream. So think of a scenario where you're generating a scene. It starts with the prompt. An empty glass sits on a wooden table. You're maybe 15 seconds into the video and you decide you want something to happen. You change the prompt to dark coffee streams into the empty glass.
Traditionally, that switch would either cause a really jarring cut or the model would just ignore the previous context completely.
It's exactly.
Yeah.
With the reward forcing, the architecture supports this seamlessly. When the new prompt comes in, the model just clears the previous cross-attention cache and recomputes with the new prompt. The critical part is that the EMA Sink maintains that compressed long-term context of the table and the environment, which ensures the transition is seamless and coherent and tied to the historical visual context, all while the model instantly accepts the new dynamic instruction. That is a massive leap for real-time creative control.
This has been a truly insightful look into the engineering of high-performance streaming video generation. Reward forcing successfully tackles motion stagnation by leaning on two major pillars: the context-aware EMA Sink that dynamically maintains history with OPER efficiency, and the motion-prioritizing Re-DMD, which refines the distillation objective using these efficient RL principles.
This work absolutely sets a new standard for balancing high visual fidelity and robust, engaging dynamic motion in a real-time setting. For you, the researcher or engineer listening, this establishes a really powerful, validated pathway for building truly dynamic, interactive virtual worlds. It shows the immense power of integrating these reward-weighted regression reformulations to efficiently guide generative model distillation, giving us precise custom quality controls that, generic distributional matching could never provide.
And as we reflect on these efficiency breakthroughs, we have to consider the scale and speed that this opens up for content creation. This increased speed and accessibility democratizes video synthesis, which is fantastic for creators and researchers who have limited computational resources. However, the very efficiency that makes this such an important innovation, the ability to generate high-quality, complex video instantly and cheaply, also lowers the barrier for misuse, whether that's creating deepfakes or spreading misinformation. So given that faster, more efficient generative models like reward forcing are an inevitable part of technological progress, the question we should be asking ourselves is, how can the AI community ensure that foundational research of this caliber is always paired with mandatory, built-in safeguards like provenance tracking and watermarking integrated right into the architecture itself? That is arguably the key piece of innovation we still desperately need to figure out as we keep pushing the limits of speed and fidelity.